In the last video, we had a look at sine and cosine graphs and how they were sort of generated, and we explored domain and range of sine and cosine, and we also had a look at domain and range of the tan graph as well, and we saw pictures of those. So let me just quickly pop those in as well. So there's the sine and cosine graph, and you can see they're the same sinusoidal wave, but cosine starts here at 1 and then goes around, and sine starts here, but they're basically the same. And then we've got same shape, just shifted, and we've got y equals tan x as well. So these are the base graphs. So sine goes from 0 up to 1, then down to -1, and then back to 0 again over 2 pi. And we talked about the fact that sine, cosine, and tan are periodic functions, which means that they repeat after a certain length. So in this instance, 0 to 2 pi is when it starts repeating. Or I can go peak to peak. The distance between here and here is 2 pi. The distance between here and here is 2 pi. The distance between here and here is 2 pi. So from one point to the same position again is always the same length, 2 pi, and it repeats forever in both directions. So we've got this sort of lovely sinusoidal shape. Cosine has this sinusoidal shape as well. But just looking at the period, it's the same from 0 to 2 pi, it starts repeating, or 2 pi in length. From peak to peak, point to point is 2 pi in length. Importantly, I suppose, when you're looking at the shape, you can sort of see it's kind of like a tulip shape sort of thing, maybe, or the top of a wine glass, that kind of shape, just over 0 to 2 pi. And then tan looks vastly different. Tan is sort of stripy, and we've explained why. I explained why in the last video, so I'm not going to go through it again. And we've got an asymptote. Every pi on 2 is an asymptote. I'll do the first couple just so that we can sort of see them. X equals pi over 2, and x equals 3 pi over 2. And I'll just colour them so that they stand out. There we go. And I could keep on going on and on and on and on. So that's the basic thing. And we can see here that from point to point, it's a period of pi, or from this point to this point, it's a length of pi here. So it's periodic over pi. Okay, so I just wanted to spend a brief moment or two talking about how to graph them, or how to find the function given the graph. So we're going to start with the base functions as well. Here's the base graph, sine. So I start by drawing my function here. I'll just have to refresh the screen. It's not working. Give me a second. There we go. Just catching up. So I try to do it in kind of one easy move, I suppose, and keep it as neat as possible. So try and do maybe like 1/2 like this, and then repeat it again but underneath, and try and keep it as even as possible, like so. I reckon I could do probably a slightly better job like that. So I'm trying to keep it nice and even over those to draw that sinusoidal wave. Once you've drawn it, then put in the x-intercepts. So we know that the end of it is 2 pi. And then if you halve the distance here, you can put in where it hits the x-axis again, pi here. And then for the top and bottom, maximum, minima, I halve it again. So it's pi on 2, and it's 3 pi on 2. And then we're done. Oh, no, not quite done, actually. We should put the maximum and the minimum in as well, like so. 1 and -1. And that's the graph done. I know it's not perfect, but it's not too bad. For cosine, again, we start here and we sort of go down like so. And then I'm going to do the cup kind of thing behind, underneath, sorry, like so. And then I'm going to go back up again, like so. Okay, not perfect again, but it's okay. And then we can apply the same sort of thing. The period is 2 pi, so I put 2 pi over here. Halfway along is pi, so that would be the minimum. And then halfway along again is pi on 2. That's where it cuts through the x-axis. and 3 pi on 2. That's where it cuts through the axis again. Just a reminder again, 90 degrees, 180, 270, 360. Put in, oops, the maxima and minima, 1 and -1, and we're done. So I draw the graph first, then put all the critical information in. For tan, I would start with the asymptotes first. So there's one at 90 degrees, or pi on 2, and there's another one over here at 3 pi on 2, like so. So note that I'm just drawing it over 0 to 2 pi. You have to be really careful to read what that says. It might ask you to do it for between minus pi and pi or something else. So just be careful that you are drawing it according to the appropriate domain that you've been given. So now I'll draw my graph in. The first part of it is just going from 0 and then up towards infinity. And then the next part goes to the middle and then up again. And then the next part goes from negative infinity back to 0 here, and that's where it starts again. Okay, so that's over 2 pi, I should say. So I've got double the period here. One period is pi. Oops, did the wrong color then. So there's pi there. This is 2 pi here. The asymptotes are halfway again, so 3 pi on 2 and pi on 2, and we're done. There's no maxima and minima for a tan graph, so we're kind of done. All right, so that's basically how you'd go about drawing them. So for sine and cosine, I would draw my axes, then I would draw my curves, then I would put in my x-intercepts and my maxima and minima. For tan, I would put in my asymptotes, and then I would draw the graph, and then I would put in my x-intercepts and not worry about a maximum minima because there isn't one. Okay, slide 16 talks about transformation. So if these are the three base graphs, we know there are always three kinds of transformations that we can apply to a base function to get a new function and therefore a new graph. We have dilations, which are stretches towards or away. That we have translations, which are shifts left or right or up and down, and we have reflections. Now, when it comes to sine, cosine, and tan, although you can do any combination of those three kinds of transformations, in Maths Methods Foundation, we're only interested in two of them. One of these words refers to dilation of the output, and one of these words refers to dilation of the input. We also look at reflections too, but I've got these two words down here because they are new words for periodic functions. So as a bit of a start, I'll get you to pause the video and have a go at putting these two functions here into Desmos and see what the impact is on the function. But I've given it away a little bit up here. Output dilation, same direction of the y-axis. So see what they do and then come back. So pause the video now. Okay, hopefully you pause the video. Here's Desmos. I'll turn off these ones here. I'll pop the sine function in again. So there's the basic sine graph here from 0 to 1, down back to 0, down to -1, back to 0, and so on. So if I put a 2 in front of it, we can see that the intercepts don't change. It's 0, pi, and 2 pi. But the graph has stretched up to 2 instead of 1, and it's stretched down to -2. So it's a vertical stretch. Okay, it's a vertical stretch. It stretches that way. So the formal way you say in Maths Methods is it is a dilation in the direction of the y-axis. And it means in the same direction as the y-axis. The y-axis goes up and down, and so does the stretch. So it's a dilation by factor of 2 in the direction of the y-axis. If I go to a half instead, we can see that it is now shrunk. 0, pi, and 2 pi. The x-intercepts are the same. The period hasn't changed. All that's changed is that it now goes up to a half and goes down to minus a half. So it has vertically shrunk, and we say it's a dilation by factor of a half in the direction of the y-axis, in the same direction as the y-axis. So it shrunk this way. Okay, so that's basically that. So we can see that changing the value before multiplying sine of x by a value will cause a dilation. Every point is either closer to or further away from the x-axis, which is why we say it's a dilation in the same direction as the y-axis. Okay, so this is what amplitude is. It's the value that we multiply the function by. So if I sketch this, I would start by drawing my axes. Let's just assume it's between 0 and 2 pi. We haven't changed the period, and so I'll just draw my function like so. The period hasn't changed, so that's 2 pi. That's pi, and that's 0. Halve it again. Pi on 2, halve it again. 3 pi on 2. And there we have our graph drawn, but our maxima and minima have changed. It is now 2 and negative 2. Okay, so this is for y equals 2 sine of x. Okay, and we're done. If I was doing the other one, there's my axes, draw my curve as good as I can. That was a pretty poor job by me, but nevertheless, put my x-intercepts in, put my maximum minima in by just continuing to halve, like so. Now it says half x there, so I put my half here and negative a half there, and I'm done. Okay, I'll just label it y equals a half sine x. This is y and x. I should do the same thing on my other graph as well. And we are done. I might just do a bonus graph, y equals negative 3 sine x. So this includes a reflection. The minus means there's a reflection as well. So I'd start off with my graph. I would then draw in my function, but it's reflected, which means that every point here is now going to be underneath, and every point here is now going to be above. So we are literally drawing a mirror image by going down and up, and then up and down, like so. Again, I've done a pretty quick drawing here, so you could take more care than I'm doing. 2 pi, halve it to go to pi, halve it again for the minima here, and halve it again here for the minima here, and we're done. So, in summary here, we've talked about amplitude on this page. The amplitude is the distance from the center of the blue graph up to the maxima. Okay, so it's a length of 2 here, or a length of 2 from here down to the minima as well. So it's the max. It's the distance from here to here. So note that it does not include the sign negative. So sorry, I should have put negative 3 here and positive 3 here as well. So note that it does not include the negative sign. It just includes the value. So the amplitude is 3. Now we don't do vertical shifts in this class, but if we did, we would have this graph going upways or downways. And if we did that, you would note that if I shifted this whole thing up by 4 units, this maximum here would be 4, and then it would go like this, and then down to 0, then back up again. And so do note that it's not just what this value here is, but it's the distance from the start up to the maximum here. So the middle point of the graph. Now, probably the easiest way I think to think about it is have a look at the length or the height between the maxima and the minima. So the height here is 4, 2 to get to here, and then 2 more here. So if the height is 4, the amplitude is half of that, which is 2. Okay, so amplitude is half the height of the graph, and that works for sine and cosine, even though these 3 examples are sine. Okay, so that's amplitude done. The next thing we're going to have a look at is period. So the period is a dilation of the input. So let me pause the video and get a new screen up, and then we'll go from there. Okay, so you can see in this page here, I've described the period as a dilation of the input. And that means the graph changes in the same direction as the x-axis. So try these two in Desmos, and then we'll have a little chat about it. So I'm looking at cosine instead of sine for this one. So pause the video, away you go. Okay, either you have or you haven't. So let's have a look at cosine. This is the base graph of cosine. It's got that tulip shape kind of thing, but it is sinusoidal. It just starts at a different spot, I suppose. And let's see what happens when we put a 2 in front of it. You might have anticipated this already, but I'll tap on the 2. Let's try that again. This is the bit we want to do. Tap on the 2 here. And you'll see that it's concertinaed the graph. It's squished it up. So if I look at between 0 and 2 pi, it's done 1 repetition and 2 repetitions by the time it gets to 2 pi. Okay, so the effect of putting a 2 in front of the x is that it has accelerated how quickly it gets through one cycle of the graph. So to go from peak back to the peak, instead of being 2 pi, it is now pi. Okay, and then it will repeat itself again. So if I'm graphing this between 0 and 2 pi, I'll in fact have 2 cycles between 0 and 2 pi. So the period of this function, cos 2x, is pi. Okay? If I make it a half x, you might be able to figure out what that means. We should have already done it. But you can see that in order to go from peak to peak, it's now stretched it over to 4 pi. So it's a stretch in the same direction as the x-axis. It's stretched this way. Okay, so if I go from trough to trough, maybe trough is the lowest point. So trough minus 2 pi, and then back to 2 pi here. So it's got a length of 4. So the period is 4 pi. Okay, the length is 4 pi. Negative 2 pi plus 4 pi is positive 2 pi. Okay, so let's have a look at graphing those ones. These require a little bit more thought. So we've got a period that we need to sort out here. By the way, in the previous part, I was looking at amplitude. It doesn't make sense to talk about the amplitude of a tan graph because it doesn't have a maximum or minimum. But tan graph does have a period adjustment. So let's have a look at y equals cos 2x. How would I graph that? And let's assume that it's between 0 and 2 pi again. So I'll draw my axes in, and I know that the period is now pi, and so I am going to draw just 1 in as best as I can, and then I'm going to repeat that like so. Again, this is really rough. Don't do as I do, just do as I say and use a ruler and all that kind of stuff. So let's have a look over one period here. So I'm going to put pi here, and then I'm going to use the same actions as I did before, and that is I'm going to keep on splitting things in half to get the critical points. So half of pi is pi on 2, so that goes there. Half of pi on 2 is pi on 4, so that becomes pi on 4, and that becomes 3 pi on 4. I'll let you think about that, but they're basically always just the midpoints. And since I'm going between 0 and 2 pi, I'm going to do the same thing, with the endpoint here being 2 pi. Half between pi and 2 pi, that must be 3 pi here. Between pi and 3 pi, what's the halfway point of that one? 1.5 pi. So that's 3 pi on 2. And what's the halfway point between 3 pi and between, that should be 4 pi, beg your pardon. What's the halfway point between pi and 4 pi? That'd be 3 pi. Okay. So there you go. So that's all of our critical points in, and we're basically done. Should be 2 pi, sorry. I'll just erase that. I'm just getting ahead of myself. And, sometimes I make mistakes, and that's all right. So I'll say that again for this one. We've got between pi and 2 pi, we need to split the difference between pi and 2 pi. So we've got 1 pi in length there. So this here should be 3 pi on 2 in the middle. That's 1.5 pi. And then we're going to split that again. So we've got 3/4 of pi. Between pi and 3 pi on 2. Just erase these. Zoom up a little bit. Okay. I really should just redo the video, but I don't mind you seeing me make mistakes because that's the reality of how it works in essence. Okay, so I've got pi here and I've got 3 pi on 2. So what you need to do is you need to work out the halfway point between pi and 3 pi on 2. So what you can do is you can sort of say, well, pi is 2 pi on 2, and then we've got 3 pi on 2. So what's the midpoint between those two? Okay, that's what you need to work out. Okay, so if you think about it, there's no whole number in between those, so maybe I could talk about 4 pi on 4 and 6 pi on 4, so I'm just using my fractions, and now I can see there's 5 pi on 4 in between. So I label that with 5 pi on 4, and now I can do the same thing between 3 pi on 2 and 2 pi. I can go 3 pi on 2, and then I'll have 4 pi on 2, that's 2 pi, and there's nothing between, no whole number between 3 and 4, so I'll just find equivalent fraction. 6 pi on 4 and 8 pi on 4, and so we've got 7 pi on 4, like so. And I'll just make that a bit bigger here as well. So that's how we work out our midpoints. It's a bit tricky, isn't it? But it's not too bad. Let's do it again. This time let's do y equals cosine of a half x. And because it's going to be a bit yucky if we don't do it, I'll just make it between x and 4 pi. Draw my graph in, using a nice ruler, of course. Draw, excuse the background noise, oops, draw cosine. The little tulip kind of shape there. Put the end point here, which is 4 pi, and then keep splitting. So there's 4 pi, so the middle must be 2 pi, halve it again to make pi, and make this one 3 pi. So that was a much faster one to do, wasn't it, than the other one? So that's a change in period here. Okay, so a couple of things I wanted to sort of get you to sort of think about. How do we work out the period if we're just given the graph without drawing the picture first, I suppose? And I guess the important thing to do is that you need to know the base periods first. So sine is 2 pi, cosine is 2 pi, and tan is equal to pi. So if we have, for example, if we're told the sine of 3x and we're asked what the period is, well, we're going to, since it's happening 3 times as fast, we're going to be having a smaller period. So what we do is we take the period, we take its original, or its base length, which is 2 pi, and divide it by the value of x. And so the new period is 2 pi on 3. Okay? I'm going to flick over to the next page and do a few more calculations. I'm going to run out of slide parts, but that's okay. So it's a big blank screen. So if I had the tan of 5x, like so, then the period would be pi, because that's the base length, and I'm going to divide it by 5. So the new period would be pi on 5. Okay, and it would repeat 5 times within pi. If I had the sine of a half x, Then the period, it's a bit more trickier to work out, but it's not too bad, is 2 pi, and then I divide it by a half. And that's the same as dividing by a half like that. And that's the same as multiplying it by 1 on 2. Put 2 pi over 1 so it's clear here. The 2's cancel out and I'm left with pi. So the period for sine of half x is equal to pi. One last one I'll show you. Let's just say it's cos of pi on 12x. So there's a pi in the period length. This is still okay. The period is 2 pi over pi on 12. So that's 2 pi on 1 multiplied by 12 over pi. So the pi's would cancel out and I'd be left with 24. Now the reason why I showed you this one is because this funny looking function here actually ends up with a nice whole number like 24. So this cosine graph here would end up giving you a cosine graph over a period of, say, 24 hours. So if I was doing tidal heights or something like that, then, and I wanted to measure it in hours of the day rather than in 0 to 2 pi, then using something like this in my cosine function would allow me to model it over a length of time rather than in pi or whatever else. So there you go. So I'll leave this video here because it's long enough as it is. In the next video, I will go through some graphs and show you how you can work out the function given the graph.